Hi. This is Transaction Processing Concept Lesson. Several topics will be covered throughout this learning session. The topics are Introduction to Transaction, Single User vs Multi-User Systems, Read and Write Operations of a Transaction, Problem in Concurrency Operations, Types of Transaction Failures, and Serializability of Schedules.
Transaction is a logical unit of database operation. Example of transaction is a transfer of $100 from a checking account to a savings account. Characteristic of transaction operations: reads, database retrieval, such as SQL select. Writes, modify database, such as SQL insert, update, delete. Transaction processing systems is a systems with large databases and hundreds of concurrent users, and require high availability and fast response time. Single user DBMS is at most one user at a time can use the system. An example of a single user is home computer. Multi-user DBMS is where many users can access the system, database, concurrently. Example, airline reservation system. Multi-programming allows operating system to execute multiple processes concurrently. Executes commands from one process, then suspends that process and executes commands from another process, etc. The slide shows the illustration of interleaved processing that involved processes A and B executing concurrently in an interleaved fashion. Parallel processing involved processes C and D executing in parallel. During the execution of transaction, logical units of database processing is formed. The begin and end transaction statements is used to specify transaction boundaries. A transaction may involve the read-only transaction, the read-write transaction. Database represented as collection of named data items. Size of a data item called its granularity. Data item cost of record. Disk block. Attribute value of a record. Transaction process. Two processes involved in transaction. Read item, X. Reads a database item named X into a program variable named X. Process includes finding the address of the disk block, and copying to and from a memory buffer. Write item, X. Writes the value of program variable X into the database item named X. Process includes finding the address of the disk block, copying to and from a memory buffer, and storing the updated disk block back to disk. The slides show two sample transactions, A. Transaction T1, B. Transaction T2. Read set of a transaction. Set of all items read. Write set of a transaction. Set of all items written. A database buffer is a temporary storage area in memory used to hold a copy of a database block. When the database engine reads a database record, it stores the block that contains that record in a database buffer. DBMS will maintain several main memory data buffers in the database cache. When buffers are occupied, a buffer replacement policy is used to choose which buffer will be replaced. Example policy: transactions submitted by various users may execute concurrently. Access and update the same database items. Some form of concurrency control is needed. The lost update problem occurs when two transactions that access the same database items have operations interleaved. Results in incorrect value of some database items. There are four types of concurrency problems: dirty read problem, unrepeatable read problem, lost update problem, and phantom read problem. This read is called as dirty read because there is always a chance that the uncommitted transaction might roll back later. Thus, uncommitted transaction might make other transactions read a value that does not even exist. This leads to inconsistency of the database. Note: dirty read does not lead to inconsistency always. It becomes problematic only when the uncommitted transaction fails and rollbacks later due to some reason. The diagram shows an example of the dirty read situation. Here, T1 reads the value of A. T1 updates the value of A in the buffer. T2 reads the value of A from the buffer. T2 writes the updated the value of A. T2 commits. T1 fails in later stages and rolls back. In this example, T2 reads the dirty value of A written by the uncommitted transaction T1. T1 fails in later stages and rollbacks. Thus, the value that T2 read now stands to be incorrect. Therefore, database becomes inconsistent. Unrepeatable read problem is the problem occurs when a transaction gets to read unrepeated, i.e. different values of the same variable in its different read operations even when it has not updated its value. The diagram shows an example of the unrepeatable read problem situation. Here, T1 reads the value of x, equals 10 say. T2 reads the value of x, equals 10. T1 updates the value of x, from 10 to 15 say, in the buffer. T2 again reads the value of x, but equals 15. In this example, T2 gets to read a different value of x in its second reading. T2 wonders how the value of x got changed because according to it, it is running in isolation.
Lost update is the problem occurs when multiple transactions execute concurrently and updates from one or more transactions get lost. This problem occurs whenever there is a write-write conflict. In write-write conflict, there are two writes, one by each transaction on the same data item without any read in the middle. The diagram shows an example of the lost update problem situation. Here, T1 reads the value of A equals 10 say. T1 updates the value to A equals 15 say, in the buffer. T2 does blind write A equals 25, write without read, in the buffer. T2 commits. When T1 commits, it writes A equals 25 in the database. In this example, T1 writes the overwritten value of x in the database. Thus, update from T1 gets lost.
Phantom read is the problem occurs when a transaction reads some variable from the buffer and when it reads the same variable later, it finds that the variable does not exist. The diagram shows an example of the phantom read situation. Here, T1 reads x. T2 reads x. T1 deletes x. T2 tries reading x but does not find it. In this example, T2 finds that there does not exist any variable x when it tries reading x again. T2 wonders who deleted the variable x because according to it, it is running in isolation. The slide shows the incorrect summary problem. It is occur when concurrent execution is uncontrolled. The example given that T3 reads x after n is subtracted and reads y before n is added. A wrong summary is the result, off by n.
Why recovery is needed. The slide shows some terms that need to be understood. Committed transaction. Effect recorded permanently in the database. Aborted transaction. Does not affect the database. Types of transaction failures. Computer failure, system crash. Transaction or system error. Local errors or exception conditions detected by the transaction. Types of transaction failures. Concurrency control enforcement. If a transaction causes deadlock or violates serializability, then concurrency control schemes will force the transaction to abort. Disk failure. Some disk blocks may lose their data because of a read or write malfunction or because of a disk read/write head crash. This may happen during a read or a write operation of the transaction. Physical problems or catastrophes. Example: transaction error. This error happens when user aborts the transaction, or logical programming error, or some operations like division by zero, etc. Example: computer failure, system crash. A hardware, software, or network error may cause a computer to fail or hang during an ongoing transaction. System must keep sufficient information to recover quickly from the failure. Disk failure or other catastrophes have long recovery times. System must keep track of when each transaction starts, terminates, commits, and/or aborts. There are 5 types of processes. Begin transaction, read or write, end transaction, commit transaction, roll back, or abort.
The slide shows the state transition diagram illustrating the states for transaction execution. Once the transaction begins, the database will be in the active state. 2 processes involved to keep database in active state is read and write. The aborting process can happen after the active state and put the database in terminated state. When the transaction ends, the database will be partially committed before it is in fully committed state and later put the database in terminated state. The aborting process can happen after the RDLI committed state and put the database in terminated state. System log keeps track of transaction operations. Sequential, append-only file. Not affected by failure, except disk or catastrophic failure. Log buffer. Main memory buffer. When full, appended to end of log file on disk. Log file is backed up periodically. Undo and redo operations based on log possible. Commit point of a transaction. Occurs when all operations that access the database have completed successfully. An effect of operations recorded in the log. Transaction writes a commit record into the log. If system failure occurs, can search for transactions with recorded start_transaction but no commit record. Force writing the log buffer to disk. Writing log buffer to disk before transaction reaches commit point. There are number of policies and method for DBMS-specific buffer replacement. Page replacement policy. Selects particular buffers to be replaced when all are full. Domain separation, DS, method. Each domain handles one type of disk pages. Index pages. Data file pages. Log file pages. Number of available buffers for each domain is predetermined. Hot set method. Useful in queries that scan a set of pages repeatedly. Does not replace the set in the buffers until processing is completed. The DBMS method predetermines the pattern of page references for each algorithm for a particular type of database operation. Calculates locality set using query locality set model, QLSM. It is important to ensure that the database remains consistent before and after the transaction. To ensure the consistency of database, certain properties are followed by all the transactions occurring in the system. These properties are called as ACID properties of a transaction.
The slide shows the desirable properties of transactions, ACID. Atomicity is to ensure that either the transaction occurs completely or it does not occur at all. To ensure that no transaction occurs partially, all or nothing rule. Consistency is to ensure that integrity constraints are maintained. Isolation is to ensure that multiple transactions can occur simultaneously without causing any inconsistency. Durability is to ensure that all the changes made by a transaction after its successful execution are written successfully to the disk.
Levels of isolation. Level 0 isolation does not overwrite the dirty reads of higher level transactions. Level 1 isolation has no lost updates. Level 2 isolation has no lost updates and no dirty reads. Level 3, true, isolation has repeatable reads. In addition to Level 2 properties. Snapshot isolation. Characterizing schedules based on recoverability. Schedule or history. Order of execution of operations from all transactions. Operations from different transactions can be interleaved in the schedule. Total ordering of operations in a schedule. For any two operations in the schedule, one must occur before the other. Two conflicting operations in a schedule. Operations belong to different transactions. Operations access the same item X. At least one of the operations is a write_item, X. Two operations conflict if changing their order results in a different outcome. Read-write conflict. Write-write conflict. Recoverable schedules. Recovery is possible. Non-recoverable schedules should not be permitted by the DBMS. No committed transaction ever needs to be rolled back. Cascading rollback may occur in some recoverable schedules. Uncommitted transaction may need to be rolled back. The slide shows several types of schedule based on recoverability. Cascadeless schedule. Avoids cascading rollback. Strict schedule. Transactions can neither read nor write an item X until the last transaction that wrote X has committed or aborted. Is a simpler recovery process. Restore the before image. Cascadeless schedule. Avoids cascading rollback. Strict schedule. Transactions can neither read nor write an item X until the last transaction that wrote X has committed or aborted. Simpler recovery process. Restore the before image. Serializable schedules. Always considered to be correct when concurrent transactions are executing. Places simultaneous transactions in series. Transaction T1 before T2, or vice versa. The slides show 4 examples of serial and non-serial schedules involving transactions T1 and T2. A. Serial schedule A, T1 followed by T2. B. Serial schedule B, T2 followed by T1. C. 2 non-serial schedules C and D with interleaving of operations. Problem with serial schedules. Limit concurrency by prohibiting interleaving of operations. Unacceptable in practice. Solution: determine which schedules are equivalent to a serial schedule and allow those to occur. Serializable schedule of n transactions. Equivalent to some serial schedule of same n transactions. Result equivalent schedules. Produce the same final state of the database. May be accidental. Cannot be used alone to define equivalence of schedules. The slide shows 2 schedules that are result equivalent for the initial value of x equals 100 but are not result equivalent in general. Characterizing schedules based on serializability. Conflict equivalence. Relative order of any 2 conflicting operations is the same in both schedules. Serializable schedules. Schedule S is serializable if it is conflict equivalent to some serial schedule S. The slide shows the algorithm for testing conflict serializability of a schedule S. 1. For each transaction Ti participating in schedule S, create node labeled Ti in the precedence graph. 2. For each case in S where Tj executes a read_item, X, after Ti executes as write_item, X, create an edge, Ti to Tj, in the precedence graph. 3. For each case in S where Tj executes a write_item, X, after Ti executes as read_item, X, create an edge, Ti to Tj, in the precedence graph. 4. For each case in S where Tj executes a write_item, X, after Ti executes as write_item, X, create an edge, Ti to Tj, in the precedence graph. 5. The schedule S is serializable if and only if the precedence graph has no cycles. The slide shows constructing the precedence graphs for schedules A to D to test for conflict serializability. A. Precedence graph for serial schedule A. B. Precedence graph for serial schedule B. C. Precedence graph for schedule C, not serializable. D. Precedence graph for schedule D, serializable, equivalent to schedule A. How serializability is used for concurrency control. Being serializable is different from being serial. Serializable schedule gives benefit of concurrent execution, without giving up any correctness. Difficult to test for serializability in practice. Factors such as system load, time of transaction submission, and process priority affect ordering of operations. DBMS enforces protocols. Set of rules to ensure serializability. View equivalence and view serializability. View equivalence of two schedules. As long as each read operation of a transaction reads the result of the same write operation in both schedules, the write operations of each transaction must produce the same results. Read operations said to see the same view in both schedules. View serializable schedule. View equivalent to a serial schedule. Conflict serializability similar to view serializability if constrained write assumption, no blind writes, applies. Unconstrained write assumption. Value written by an operation can be independent of its old value. Debit-credit transactions. Less stringent conditions than conflict serializability or view serializability. There is no explicit begin_transaction statement. Every transaction must have an explicit end statement. Commit. Rollback. Access mode is read-only or read-write. Diagnostic area size option is the integer value indicating number of conditions held simultaneously in the diagnostic area. Table in the slide shows the possible violations based on isolation levels as defined in SQL. For the read-uncommit isolation level, it is possible to be happen in the dirty read, non-repeatable read, and phantoms types of violation. The read committed can occur in the non-repeatable read and phantoms, whereby repeatable read can occur in phantoms type of violation. However, in serializable isolation level, none of violation types can be happen. Snapshot isolation is used in some commercial DBMSs. Transaction sees data items that it reads based on the committed values of the items in the database snapshot when transaction starts. Ensures phantom record problem will not occur. In this lesson we have learned about single and multi-user database transactions, uncontrolled execution of concurrent transactions, system log, failure recovery, committed transaction, schedule, history, defines execution sequence, schedule recoverability, schedule equivalence, and serializability of schedules.